So I wanted to share what I do covering UV spectroscopy, which I think is a kind of a interesting technique to study composition, space weathering, and also look for activity on some of these worlds that we're going to with these missions. I'll talk about ocean worlds and also a little bit for this space policy class, some of the work that I'm doing on planetary protection. So in terms of the UV, to get into the details of it, we tend to break it down into about 4 ranges. Some people think of UV as just being kind of anything sort of short word of the visible wavelengths. But technically we can go as deep as the EUV, which goes down to about 10 nanometers, all the way up to the near UV, which is 300 to 400 nanometers. So then that's the range that's definitely just short word of the visible wavelengths. Everything short word of about 300 nanometers is not observable from the ground. So from ground-based telescopes due to atmospheric absorptions in the Earth's atmosphere. So most of what have been working on is space-based telescopes, the International Ultraviolet Explorer, for instance, which is no longer in operation, and Hubble Space Telescope. And then also deep space missions like Galileo to the Jupiter system, Cassini to the Saturn system, Messenger to Mercury had a UV instrument, and then back in the older days, the Mariner 6, 7, and 9 missions to Mars had some of the first UV instruments on board. And then currently, we have the Lunar Reconnaissance Orbiter, which is in orbit at the moon, and it's got a UV instrument, and it's been orbiting since 2009. New Horizons and Rosetta. New Horizons went to Pluto, as you may know, and it's still going. It's way out in the Kuiper Belt. And Rosetta orbited near the comet Churyumov-Gerasimenko with a UV instrument. Most of what I have focused on is UV composition of surfaces. So you can do a lot in the UV, looking at atmospheres and emissions from aurora, for instance. I focused on bodies, airless bodies. Again, looking at space weathering effects, so the effects on composition and chemistry from charged particle bombardment, like solar wind irradiation, and micrometeoroid bombardment. There's diagnostic absorptions that can complement spectroscopic measurements at the more traditional sort of vis near IR wavelengths. And we can also use it to study grain size differences that might, for instance, be diagnostic of plume depositions. And then we can also detect plumes directly as well, that I'll talk about. So here's some of the icy moons that we talk about. Europa on the upper left, which is one of Jupiter's moons. The biggest moon in the solar system, Ganymede, another one of Jupiter's moons, and Callisto in the top row. And then Enceladus and Titan, Saturn's moons, and these are not to scale here. Titan is technically an icy moon. Of course, it's an icy moon, but it actually has a thick atmosphere that we can't see in this image. So all of the UV studies that we have done of Titan focus on the upper atmosphere because the UV light can't make it through the surface. But I include it here since it is an ocean world that I'll also be talking about. Oh, and just so you know, so everybody's on board, Earth's moon that we all are familiar with, that has a diameter of about 3474 kilometers. So all of these moons here are, in the size range of Earth's moon, except Enceladus is significantly smaller. It's only about 500 kilometers across, which is one of the reasons it was a little surprising that it's so active, as we'll talk about. But these are all ocean worlds. These are the interior models, kind of cutaway cartoons of all of these worlds that we now know have icy shells of some thickness overlying a liquid water layer. And for some of them, like Ganymede and Callisto, there's below the liquid water layer, there's an ice layer, or for Europa and Enceladus, there's a rock layer beneath the liquid water ocean, which is really interesting and important because that rock layer can help directly provide heat to the ocean to keep it liquid, and also can be a source of nutrients for the ocean that can contribute to its habitability if it is habitable. So let's talk about Europa's ocean. This was the first ocean world that was ever discovered. This is a picture from the Voyager 2 flyby back in 1979. So this is when the first clues came to Earth about how interesting this moon was and that something could be going on because it's covered in cracks. It's not covered in craters like our moon. And we knew that it was ice rich from spectroscopic information, providing absorption features that show us that there's water ice covering the surface. But seeing all of these cracks across the surface made folks think something must be going on there. And the fact that there's very few impact craters. And then here's, the kind of the iconic Europa image from the Galileo mission that arrived at Jupiter in 1995. And again, we can see that the icy crust is broken up by cracks and fissures, but also by discoloration in this is kind of a false color enhanced image, but there is reddish material primarily on the trailing hemisphere. So that's the hemisphere. I should mention Europa and all the moons that we're talking about are phase locked. So they're tidally locked. So they keep one hemisphere facing the direction of motion. That's the leading hemisphere. And then the trailing hemisphere is the one that's facing the anti-direction of motion. And so what happens is in Jupiter's big magnetosphere, there's a co-rotating plasma, and that all primarily hits the trailing hemisphere. And so that is probably linked to some of this red discoloration here. But Galileo also showed us close-up views of Europa's surface, giving us further hints of something going on, maybe a subsurface ocean, because there's these fractures on the surface. There may be some sort of communication, at least in the relatively recent past, with subsurface material, because at these fissures, there seems to be maybe clues to some sort of upwelling happening. Ice regions that seem to have been broken up by some sort of tectonic movement, and these chaotic regions, again, that are discolored, not freshwater ice, but it's not clear still how much that discoloration might be driven primarily by charged particle bombardment, since Europa is orbiting Jupiter within this powerful plasma environment, and how much might be due, though, to communication with an underlying layer, because you can see that there's splotches of reddish stuff. Like here, that's a kind of a chaos region, but then there's also splotches of red stuff along some of these cracks. So maybe it's some sort of combination of maybe stuff that has come up from the subsurface and then been irradiated. It still is really an open question. But those were clues that there's something happening in the subsurface, but not a smoking gun. The smoking gun, as much as we have it, came from the Galileo magnetometer. And I was talking before the talk about the Enceladus, the Cassini magnetometer measurements at Enceladus. This is a different story here at Europa with the magnetometer. The magnetometer detected an induced magnetic field at Europa. And this is based on a careful analysis of like 3 or 4 flybys worth of data, where the magnetometer sent something going on in the Jupiter field lines near Europa, and after careful analysis, realized that it must be from an induced field, almost certainly from an conducting layer, which most naturally is a salty ocean. And at the same time, the gravity measurements from Cassini, from Galileo found that based on those radio science measurements, Europa could have a subsurface liquid water ocean. So a couple of lines of evidence there. The reason that you can do this kind of magnetometer measurements at Europa is because of the wobbly magnetic environment at Jupiter. Because Jupiter is spinning around, its field is co-rotating with it, but that field is tilted by about 10 degrees with respect to the spin axis. And so as the field goes around, it's sort of wobbling like this. And if you have a conducting thing in that moving, changing magnetic field, and if you've got a conductor, then it's going to produce an induced field. Kind of like when you go through magnetic detector at the airport and you've got your keys in your pocket. It's going to be. So that's the great thing about Jupiter with its wobbly magnetic field, is that you can detect a subsurface ocean. So again, it doesn't definitely prove the existence of an ocean on Europa, but it is very strong evidence. So, oh, and then how does it, let's see, actually, do I have this? Let me see if I can do this. Why is there an ocean there? It's because it's an icy moon and it's got this strong gravitational interactions with giant Jupiter. So it actually kind of ends up flexing the shape of the body, and it kind of keeps heat conducting through this rocky layer and keeps the water and ends up being liquid and stays liquid. But it's not just Jupiter, actually. It's also a special environment in the Galilean system, because Europa, which is shown in the second blue line here, is the second of the main moons orbiting Jupiter, and it's in resonance with the other moons. So every Io is on the red line. Every 2 times Io goes around, Europa goes around once. And it's also then in resonance with Ganymede, which is on the orange line, which goes around once every 2 times Europa goes around. So you've got tugging both from constant tugging from Jupiter, and then also constant tugging from smaller moons going around repeatedly. And that's the trick to keeping the subsurface water layer liquid. Now, Enceladus is doing something different. It's providing us very clear evidence of a subsurface ocean and activity, current day activity at this much smaller icy moon of Saturn. So as I mentioned before, we came about this with the Cassini mission from a few lines of evidence, but then this is one of the visual clues that we got then a little bit later, after we found out about the activity using magnetometer and the thermal instrument and some of the in situ instruments and the UV instrument. The Saturn field is not tilted with respect to its spin axis. So you cannot do the Galileo trick that we did in the Jupiter system. The field lines at Enceladus were perturbed, but that was because of the injection of neutral material into that environment, kind of tweaking those Saturn field lines around Enceladus. But since the field is not tilted, you can't sense a conducting layer like at Enceladus like you can at Europa. Okay, so what do we do with the UV to detect the plume? And how might we do it at other bodies too? So when we look at images like this of Enceladus, what we're looking, this is a visible wavelength image, and what we're seeing is the particles, the actual ice grains. And we're seeing them because they're backlit. Like you can see that this is a very high phase image. All we're seeing is just a little crescent of lit surface there. And so the sun is on the other side of Enceladus there, and that's how we see these particles, is because the sunlight is coming through them. But when you've got the sun behind you and you're just looking at Enceladus, you can't see the plume. And that's why we didn't actually detect it with the camera until a little bit later in the mission, with the camera anyway. In the UV, you can look for plumes using emission features. You can look at reflected sunlight at FUV wavelengths and see if you can see the grains reflecting sunlight. Or you can look for absorption by the gas in the plume using Saturn as a source. So watch Enceladus go in front of Saturn and see if you can see the gas in the plume getting absorbed. Or the easiest thing to do and the most direct, which we ended up doing quite a few times throughout the mission, is using occultations by stars. And then we also did it by the sun once or twice. So, and this is where we watch a star pass behind the plume, and we are measuring that stellar spectrum, and then we watch it dip out and get absorbed as it goes behind the plume, because the plume is absorbing some of that light. So if we want to, in our stellar occultation, remember our different FUV and EUV ranges. We had an EUV and an FUV channel on the Cassini ultraviolet imaging spectrograph, or UVIS instrument. And so for stars, we use the FUV channel because the starlight cuts off in the EUV. But for the sun, if we want to use the EUV and get certain compositions like nitrogen, we can use do solar occultations. And we can also get structure in the plume by looking at EUV or FUV data, and we sum it up over time to get structure. And then the instrument also included a high-speed photometer, which didn't give us any spectral information, but it gave us very, very high resolution data that I'll show you to give us structure in the plume. Here's an example of that. So this is where, you know, when you see the plume here, there's an overall plume. And then it's made up of kind of a background gas, and then individual jets that you can see there as more spiky things. And we can see those spiky jets in the stellar occultation data. This was an occultation by the star Zeta Orionis. And again, if you start over here, here's time, we're just observing the star. This is like added up UV counts. And so it's staying pretty steady. But then when it goes behind the plume, the starlight dips out, it's getting absorbed. And then you can see some jaggedy parts in here, which are real. Because then you can compare them with where you're looking on the surface. And those are jets that are actually individually absorbing more of the stellar light. And then the star exits the plume, and then we're back up to the kind of ambient level. So you can see here that pointed out are Cairo, Alexandria, Damascus, Baghdad. Those are the locations of the jets along the line of sight of the path of the star as it's projected onto the south pole of Enceladus. So here's the south pole of Enceladus looking down, and the plume that you see and all the jets are emanating from these four major fissures on the surface. And you can see it's, can you guys see these? I don't really have a pointer, but they're labeled Damascus, Baghdad, Cairo, and Alexandria. So these four large fissures are centered on the South Pole. And this is where the plume material is all coming out. And what you can see in the black line going up this way is the path of the star projected onto the South Pole. So then we can decide, well, where are all of these kind of bite outs in the occultation profile? A, B, C, D, E, and F are shown all the way along the path here. And then we can say, oh gosh, well, look at E and F are pretty close to Damascus. C and D are pretty close to yeah, and the B is pretty close to Cairo, and A is like right on top of Alexandria. So these are jets, kind of like larger little gaps in the fissure itself, where extra amounts, and it's actually very fast, supersonic sources of gas are coming out. And that's what we're seeing in these occultations is the gas. It's not the particles that you can see in the visible images. However, those particles are being carried along by the gas jets. Okay. So I think I thought I had a stellar occultation. Maybe I've got it later on, a spectrum to show you the signature of water ice. But I'm going to transition now to looking at not plumes, but the surface of the icy moons. And this is what, when we measure the spectrum of the surface, we've got to then have something to compare to understand what we're looking at. And so we've got to make measurements of ices and different candidate materials in the lab and compare with our spacecraft data. And so here's just a sampling of some of the ices that we can compare with. One of the big ones, of course, is water ice down here. And these are a few different lab measurements of water ice. And the big thing that I want you to notice here is that there's a, no matter, even though there's variations from spectrum to spectrum, the big thing here is that there's a big absorption edge here. It's at about 165 nanometers. So that's squarely within our FUV range and with our FUV channel on the Cassini UVIS instrument. Ammonia here, NH3, also has a big UV absorption, but that's at a longer wavelength. That's at about 200 nanometers. CO2 has been less well studied in the lab. So we need to make some more measurements of that. And then up at the upper left, that's a model of water ice. Again, just showing you that drop off there at 165 nanometers. So this has ended up to be very important for us at the Saturnian system, because as it turns out, practically everything that we looked at there with the UVIS instrument had water in it. And this is important to do these measurements here in the UV because there's some diagnostic things. Water ice, the absorption edge that we measure is going to change in wavelength slightly depending on the grain size that we're measuring. And because these are short wavelengths, the grain sizes that we're measuring are smaller than can be observed at longer wavelengths. So in the top right panel here, this is the absorption coefficient of water ice. And all that means is that these bumps and wiggles mean that water is absorbing at different wavelengths. And some of the big ones are that you might be able to see. There's a bump at 1.5 microns, and there's a bump at 2 microns, and another one at about 3 microns. And those bumps mean that water ice is extra absorbing there. So, but then you can see at the shortest wavelength, you can see it go right up. That's where water ice is really super absorbing very steeply in the far UV. That's our 165 nanometer absorption. And water ice actually even though we know water ice is really bright at visible wavelengths like snow, in the UV, when it gets absorbing, that means that shortward of that absorption edge, it's very dark. And it's actually darker than practically everything else. So you can see on this left-hand figure here, these are reflectance spectra of different candidate materials. The water ice is shown in red. And you can see it's just going up there towards the right, and you can't even see where it goes because it gets so bright. But then shortward of that, it's actually darker than everything else. Even like These are like carbon and like carbonaceous stuff, which is very, dark, but water ice just gets really, really black at those shorter wavelengths. And that ends up being a kind of a diagnostic characteristic that we can use. Let me pause here and see if anybody has any questions. Okay. Okay. So the first time that this strong far UV water ice absorption feature was seen was using the International Ultraviolet Explorer, IUE, that I've mentioned before. And this was, again, an Earth orbiting space telescope that observed Saturn's rings. And you can see their spectrum over here on the right, pretty ratty, but it does have a strong drop off there at about 165 nanometers. And then what's also shown there is a model to compare to. So that was, and of course we know that Saturn's rings are primarily made up of water ice. So that was an important initial measurement. And then we could go with Cassini UVIS back in the system and actually measure in the upper right or spectra across the whole ring, showing how the water ice abundance varies from ring to ring. By the way, I forgot to mention here, the rings, in case you're not aware, are cleverly named the A, B, C, and D rings. These are the main rings around the planet. And with Cassini, the UVIS instrument showed that there's definitely brightness variations across the rings, where the B ring is the brightest and probably has the most water ice, actually, but with the A ring close behind. But then the innermost C and D rings actually get quite dark. And as a matter of fact, it's really even hard to see the D ring visually because it's so dark and also kind of thin. There's not a lot of material there. But anyway, I'm showing you this just to show you that 165 nanometer absorption edge there is shown to varying degrees throughout the rings, and as a matter of fact, throughout the Saturn system. Here's where we first saw it when we first when the Cassini mission first entered the Saturn system. Before it encountered the rings or anything else, it encountered one of the outermost moons, Phoebe. And Phoebe is so far out from Saturn that it's actually a captured Kuiper belt object. It looks, here's an image of it. It looks kind of like an asteroid. Some people used to think, well, maybe it's a captured asteroid, but now we know it's probably a captured Kuiper belt object. And these are a couple of images that we got from Cassini UVIS. Kind of pixelated, kind of low resolution, but it shows you the amount of water ice that's varying across the surface. And we were actually surprised to even see the water ice absorption edge in this because we didn't know how water ice rich Phoebe actually was at the time. So we had to kind of scramble to get our water ice models working and everything. But there's the absorption edge. And by the way, what you can see here is that there's a little dip there at the longest wavelengths, which we still don't quite understand, actually. I suspect that that's actually a characteristic of water ice itself, too, but we need some more lab data to figure that out. At the shortest wavelengths, water ice is so dark and there's so little solar flux to be reflected off the surface to measure that it's really actually very hard. These surfaces get very dark. There's very little light. And so what we did here was we just calculated the reflectance at solar emission lines reflected off the surface. So the solar flux isn't even really much of a continuum down at these short wavelengths, but there are emission lines, and those were reflected off the surface, and we could calculate the reflectance at those lines. But what's interesting here is remember how dark water ice is at those short wavelengths? It gets darker than everything else. You can see that Phoebe is actually not super dark there. I mean, there's error bars on there, but they're up, not down at zero anyway. And that tells us that something else other than water ice is really contributing to that brightness there, or that level of reflectance, I should say. So then in the more inner part of the inner system, after we passed by Phoebe, we came into the inner part of the system. And this is where the moons, the main moons that I have worked with anyway, Mimas, Enceladus, Tethys, Dione, and Rhea, all these moons are orbiting Saturn within the E-ring. So outside of the main ABCD rings is this broad diffuse E-ring that I don't even know if you can see very well on this graphic, but it's densest at the orbit of Enceladus. And this was known before Cassini even got there, that this E-ring is there and it's densest at Enceladus. And why is that? Nobody knew how it was sourced. But of course, it turns out that it's Enceladus, and its subsurface ocean and its geologic activity is spewing out this the water vapor, the water ice grains, and that's actually sourcing the water to the system and sourcing the E-ring. The E-ring is actually very fine water ice grains, and we're talking like half a micron, maybe a few microns. Very, very fine water ice grains, which is why it was known that, gosh, you know, how is this going to be sustained unless it's constantly being replenished? And now we know why, because it's constantly being replenished. Most of the plume material that gets erupted by Enceladus actually falls back onto the surface, most of the grains. But a lot of them are on those supersonic jets and just get ejected out into the system. And what they end up doing is all of these moons are orbiting Saturn within this E-ring. And so all that E-ring material ends up kind of coating their surfaces. And that's why they're all quite reflective. They're quite high albedo, especially compared to like the Jovian satellites. Oh, there's Enceladus contributing to the E-ring. It's pretty amazing. So if you look at spectra at the visible and near infrared wavelengths, these are the Saturnian satellites from Voyager at visible wavelengths here. And you can see that they're pretty much just flat lines. In the infrared, Enceladus has these very strong water ice absorption features. Remember, I talked about the absorption coefficient kind of having local maxima at 1.5 and 2 microns. Those are those absorption features. They're in reflectance from Enceladus. It's very close to pure water ice at vis near IR wavelengths. And again, it's because it's coated in largely because it's coated in these E-ring grains. But what we found looking in the FUV is that here's one of our initial spectra of Enceladus. It's got the strong water absorption edge. But compared to a model of pure water ice, it's much darker actually. So something is different because Enceladus looks almost exactly like water ice at longer wavelengths. So that was a clue that something must be happening spectrally somewhere between the visible and the UV. Unfortunately, we had a gap in the spectral coverage on Cassini. So the Cassini UVIS covers down to here, and then the next instrument up covers up here, visible to near infrared wavelengths. But we can use Hubble Space Telescope to kind of fill the gap, which we've done over here on the right. In the black and red points on the right-hand plot there are Cassini data. And then the blue line in between is that was kind of a preliminary Hubble Space Telescope spectrum, and then connecting with the UV spectrum from Cassini. And so the point here is that the spectrum of Enceladus looks very bright, very spectrally flat at those longer wavelengths, just like water ice does. But unlike water ice, it starts to absorb there down into the UV. Water ice itself ought to just stay very flat, very bright, right up until that water ice absorption edge of 165, where it drops off. So that tells us something else is there on the surface of Enceladus. And it's probably something that's in the E-ring, because we know that the E-ring is coating the surface. Here's some more Hubble Space Telescope data combined with Cassini data to give composite spectra actually of all of these mid-sized moons: Mimas, Enceladus, Tethys, Dione, and Rhea. And we've got a couple of hemispheres here for some of these moons too. So it's kind of a busy plot, but the point is that they all have these this absorption feature heading down into the UV of varying strengths. And so what we've done is we can use that to try to understand system-wide what is happening with this E-ring material on these moons and how is it evolving and why. So because in the UV, we're sensing just the uppermost grains of the surface, right? Because that light does not penetrate very far down. So we're just sensing the uppermost surface. And that's why the UV is a good spectral regime in which to study space weathering processes, is because any bombardment that's going on by charged particles, like in the Saturnian system, on the trailing hemispheres, you're typically going to have the cold plasma, the co-rotating plasma, bombarding the trailing hemisphere. And that usually tends to have like a darkening effect. On most of, like, let's look at Tethys. This is where you get a lot of that E-ring grain bombardment on the leading hemisphere. And we do see hemispheric variations in brightness that are consistent with charged particle bombardment and E-ring grain bombardment. And this is what we're looking at in the UV. So, and I'll just kind of cut to the chase here. What we think we're sensing in these composite spectra is evidence for non-ice material in the E-ring grains, namely probably the small amount of organics that are present in the plumes, and it gets processed and weathered by that environment. And either while it's in the E-ring itself and or after it's placed on the surfaces. Okay, so we're using that to kind of be able to study the ages of the surfaces. But let me go on to, oh yeah, because I'm totally running out of time. Let me go on to the Galilean satellites at Jupiter. And I'll just show you a few spectra from the Hubble Space Telescope. We do have, I didn't end up including any in here, but we did study with the Galileo UV instrument the surfaces of these satellites. But this is newer stuff that I wanted to show you. What's interesting here is that we're looking in the far UV with Hubble at these satellites, and we do not see that 165 nanometer absorption edge. It's just not there. So this has been kind of a puzzle. You see kind of slow upturns here in that same spectral region, but you don't see that sharp drop off. So this tells us that that Saturn system is really unique. Again, it's got that for all those mostly freshwater ice E-ring grains coating the surface, and we see that in the UV. But at the Galilean satellites, what we're seeing is the effects of that intense radiation environment there. And even though they're icy moons, they just get blasted and darkened. And so some models by some of my colleagues are showing that you can add in just a little bit in kind of an intramix, it's called. So kind of dark material mixed in with the water ice, and then which you can see visually anyway. And then that FUV absorption edge from H2O will go away. So that's what we're seeing here on Ganymede and on Europa. And then into the near UV, one interesting thing that's being done with Hubble is looking at the presence of irradiated salts. And this is seen as a clue from an absorption feature at about 230 nanometers, so a little longer wavelength than we've been talking about. And that absorption feature seems to be strongest correlated with some of the chaos regions, again, that might be connected to the subsurface ocean on the leading hemisphere, actually. And that's where you see it mostly in red there, connected with some of the chaos areas. So this is really interesting. And what I'm really looking forward to is the Clipper mission, which will get launched hopefully next year, going to Jupiter to do many flybys of Europa. And maybe Clipper will tell us whether or not there's actual activity, plume activity at Europa. So we've got clues to plume activity from UV data from Hubble again. So Hubble has used a couple different UV techniques for looking for plumes on Europa. This one up here at the upper right is in emission. So it's looking at hydrogen in emission. And so maybe that's evidence of a plume, but it hasn't been repeatable. It was like a one-time thing. But it's also done absorption experiments where it watches its transit, where it watches Europa cross in front of Jupiter to see if there's a plume in absorption. And that has also led to some hints of plume activity also. So the system at Europa is very different from the system at Enceladus. You can look for emission features at Europa because of the very intense plasma in that intense magnetic field there. There's less, the fluxes of energetic electrons that are going to do the exciting of plume gases at Enceladus aren't there at Saturn. And so we looked and we could not find any emission features with UVIS at Enceladus. But at Europa, you can do it. So that's going to be another way of sensing it. But certainly the plume activity at Europa, if it is happening, is different from the ongoing activity at Enceladus. Oh, this is kind of what I just said. So this was the one kind of positive emission experiment that they did. So maybe there's sporadic activity, maybe there's erratic magnetospheric activity. But again, interesting comparisons between Enceladus's activity and Europa's possible activity. Now back to Enceladus and thinking about its subsurface ocean, we know from the ion and neutral mass spectrometer a lot of what that plume composition is like. Again, mainly H2O, but also some CO2, nitrogen, methane, other organics in the plume. Again, some of those are going to fall back to the surface. Some of them are going to go out into the E-ring. But we also have, you know, how do we know that this is actually linked to an ocean? We have the evidence from INMS. We also have the evidence from the CDA, which is a cosmic dust analyzer. CDA detected salty grains in the plume. They detected more salty grains in close to the plume, most of which actually don't make it out into the E-ring. So again, salt-rich ice grains are gonna, you know, a good source for those is a salty ocean. But then also Cassini gravity measurements point to the presence of a localized subsurface ocean. Again, a little bit similar to the experiments that were done with Europa. So there's a lot of good evidence for the plume activity on Enceladus being linked to a subsurface ocean, and a lot of evidence that that ocean is habitable. Later on in the mission of Enceladus, the INMS measured excess molecular hydrogen, which again links to potential habitability in the subsurface ocean, because we know that excess hydrogen in Earth's ocean can be linked to sort of hydrothermal vents at the seafloor. So perhaps something like this cartoon here on the right is what is happening on Enceladus, which makes it exciting astrobiologically, and probably the best place to go in the solar system to search for life, extraterrestrial life of some form. Which brings me to planetary protection. Because if we're going to go somewhere else in the solar system and search for life, we don't want to, we certainly don't want to contaminate those measurements. So we need to make sure to send clean spacecraft and clean instruments if we're going to, i.e. not contaminated by terrestrial microbes, so that we can understand what we're measuring right then and there. But we also don't want to leave behind any terrestrial microbes for any future search for life measurements that might happen, right? And so this is all part of planetary protection. And this is all linked to the Outer Space Treaty from 1967. There's two types of planetary protection outlined there. Backward contamination, which, well, forward contamination is the one that I talked about, where you don't want to contaminate any future or contaminate the integrity of any future search for life measurements. That's forward contamination. But then you also don't want to bring back any extraterrestrial material that's uncontained to produce potentially adverse changes in Earth's environment. That's backward contamination. So the US complies with the Outer Space Treaty in implementing planetary protection requirements in its missions. And COSPAR, which is the Committee on Space Research, is an international group that provides guidelines for this. And it's got a lot of international cooperation to do so. These are teeny tiny things in here, but I just wanted to quickly, because we're running out of time, just talk about the different planetary protection categories of different missions. There's 5 categories with some categories in between, and they all, category 1 through 5, have to do with how, what restrictions you have to comply with if you want to fly a mission to a particular type of body. If it's a rocky asteroid that has absolutely no chance of harboring life or being conducive to any terrestrial life, it's probably going to be Cat 1, which means that you don't have to do very much in terms of cleaning your instruments or spacecraft unless you want to for your scientific purposes. But if you're going to Mars, if you're going to Europa, if you're going to Enceladus or any of these places where terrestrial microbes might be able to, if not proliferate, at least survive, then you're going to probably have to do some level of cleanliness before you launch from Earth. And there's also in situ techniques that you might be able to use too. So these categories for these different missions are not set in stone. This is a constantly evolving process as we learn more, as it should be. And the implementation policies that you can use to address whatever requirements you have to meet for your different missions also evolve with time. So I'm on a National Academy's Committee on Planetary Protection. So we have been actively looking at some of these policies. And then COSPAR looks at the policies and sometimes looks at our reports and says, okay, well, maybe we can consider updating our guidelines. So these are the kinds of things that mission designers who want to go to these different targets in the solar system need to be considering too. So with that, I will mention briefly what's next with Ocean Worlds. We've got Clipper launching next year. We've got the European Space Agency ESA JUICE mission, which is the Jupiter Icy Moon Explorer. That's launching later this year. And that's going to go in orbit Ganymede, but it's going to have a couple of Europa flybys. Europa lander concept has been studied. It's not currently prioritized, but it may happen at some point in future decades. And then Dragonfly, which is this one here, which is going to be really neat, going to Titan. I didn't get to talk about Titan too much, but it's got a thick atmosphere. And so Dragonfly is a quadcopter, which is really neat. And then in the decadal survey, as I mentioned, NASA's decadal survey that recently came out, the priorities for the next decade are Uranus orbiter and probe, which would be cool from an ocean world standpoint because some of those moons at Uranus might be ocean worlds. an Enceladus Orbilander flagship mission going to Enceladus, which will be really great. And then also, not flagship, but smaller levels of mission concepts to Triton, Enceladus, Titan, and Ceres are also prioritized science-wise. So it's really exciting times coming up. And hopefully we'll have UV on all these missions because it's a powerful tool. And I'm going to leave it there with this beautiful picture of ocean worlds.